Okay, so today we're going to go through sections 1.4 and 1.5. So 1.4 is sort of like, up until now we've been dealing with stuff in one dimension, right? We've had things like, you've had one variable, you have the one-dimensional number line, and we've represented solution sets as sometimes we have like solution sets of solution sets were represented as points or intervals or sets on the number line. Okay, and so what we're doing today is moving into 2 dimensions. So we're just making an extra step. So going into 2 dimensions. Okay, and for mathematicians, at least at this point, dimensions you just want to think as your number of parameters. So instead of having just one, variable, we're gonna have 2 variables, say x and y or a and b or whatever. So you've got two things to keep track of, like height and weight. That's a two-dimensional object. Okay, right. So there's nothing really exotic about having like 5 dimensions. It just means that you'll be keeping track of 5 things at the same time. So the way that this is usually represented, so something 2-dimensional is usually represented on the plane. Okay, so the plane being this sort of like imaginary, infinitely thin, flat object, right? So like a sheet of paper and extending in all directions, right? And so you've got this thing, and then you put you identify. So you've got this plane, and then you identify. So each point on the plane is identified with a pair of coordinates, a pair of numbers called coordinates. Okay, and how many of you have seen this before? Yeah, like, anybody not seen it before? Okay, so you're all familiar with the coordinate plane. Good. Right, you may know a little bit of the history. This was created, this idea of, just like how we identify the real numbers, we identify the real numbers with the number line, we identify pairs of numbers with the plane, right? So every point in here, right, is associated with some pair of numbers, right? There'll be some x here, and then some y here, right? So you say, what pair of numbers? You drop a line to this axis, and you say drop a line to this number line. You say what number is that? And you drop a line to this sideways number line, and you say what number is that? Right? And then you call this point x comma y. Right? That's the idea of the coordinate plane. Everything just like here. Every number is identified with a point on the line. Here, every pair of numbers is identified with a point on the plane. Okay, this may seem like something pretty natural, but it was actually really revolutionary when Descartes thought of it, right? Because what it allowed him to do was take the ideas of geometry and then put numbers on them, right? So before that, when you think about geometry, how many of you had Euclidean geometry in high school? Some of you? Okay, so when you're thinking about geometry, you're talking about triangles and parabola and these sorts of things. But parabola you get by slicing through cones and this sort of stuff. But Descartes was the one who created so-called analytic geometry, where you say, oh, okay, I can actually identify these things with numbers. And the story is that he invented that. He thought this idea struck him as he was lying in bed one night and was watching a fly or a moth or something fly around his room, and realized that the position of the moth could be specified by its distance to each of the walls. right? So, okay, look at the distance to that wall, look at the distance to that wall, and you've got these pair of numbers identified with the position of the fly, right? And so this, you know, kind of small idea, it seems, you know, obvious in hindsight, but it was really revolutionary at the time. Okay. Okay, so yeah, so the plane. Okay. Okay, yeah, let's go. Okay, so right, so we've got instead of single numbers, right? Instead of single numbers, we've got pairs of numbers, and just like we have a way of defining distance on the number line, we have a way of defining distance in the plane. How did we define distance in the number line? Anybody want to remind me? If I've got 2 points, x and y, in the number line, how did we define the distance between them? The difference between x and y? So the difference between, Manuela?
Would it be the difference between y?
The difference between y and x? Which one is it? Y and x or x and y? Well, it depends on which one is to the right, right? So you take the bigger one minus the smaller one. But an easier way of saying that is you take the absolute value of the difference, and then it doesn't matter which is on the left or which is on the right, right? Because if x is on if x is on the left, you're still going to get the positive distance between them when you take the absolute value. So this, recall, was the distance between x and y, right? And in the plane, there's a distance formula, right? So if we have AB here and XY here, you know, what's the distance formula between 2 points in the plane? Can anybody tell me? Y equals mx plus b. Where is m and where is b? Oh, here's a b and here's a y. But you gotta. So I think you're thinking about something a little bit different. Anybody? Amy? What? The Pythagorean Theorem. Okay, so yeah, so you'd say, well, to get the distance here, I want to find this length, right? The distance is the length of this line segment, right? So how do you find the length of the line segment? You can use the Pythagorean Theorem. You say, okay, let's draw a vertical line here and a horizontal line here. That gives us a right angle, right? That gives us a right angle. Right? So we need to figure out, let's call this thing D, right? To figure out D, we need to know this length and this length. Okay? Well, what is this length here? If we think about the real line, so if we think about the real line, this is A, and what is this? If this is A, what's this thing here? X. This is x, right? So what's this length here? What is this distance? It's x minus a. Well, the absolute value of x minus a, let's say. Okay, because I don't know, maybe a is over here. Maybe my points are over here. Who knows? Okay. And then what about this distance here? The distance between here and here, what would that be? Take 10 seconds and write something down. See if you can figure it out. What's the distance between this and this? Okay. Here's another number line, the vertical number line. Turn to somebody nearby. Tell them what you're thinking. Talk with a partner. Okay, what is it? Absolute value of y minus b. Great. So absolute value of y minus b, right? So this length is the absolute value of x minus a. This length is absolute value of y minus b. So by the Pythagorean theorem, the distance. So this is the distance formula, right? The distance between 2 points A, B, and xy is, well, it's going to be the square root of the sums of the squares, right? So x minus a quantity squared plus y minus b quantity squared, right? Right, because that's the hypotenuse of this right triangle, and we know the lengths here. Is that clear? Anybody have questions about that? Okay. And if you want, probably the way you've seen it is without the absolute values, right? Because if you take this number and square it, you're going to get a positive number anyway, right? So you don't really need these absolute values, but it's kind of nicer to keep them in because it makes it clear the connection with the Pythagorean theorem, right? This is a distance. You got this distance squared plus this distance squared, this, and you take the square root. That's the Pythagorean theorem. Okay, right? This is the distance between this and this, and the second one is the distance between this and this. Okay, so for example, if I ask you for the distance between say 8, 3, and -2, 1, what would that be? Take 30 seconds, 20 seconds, and write it down, please. What's the answer? Or just do it in your head. Okay, turn to somebody nearby and say, this is what the distance is. Oh, people are still working. Okay, now turn to somebody nearby and talk with them. Okay, so what's the answer? What's the answer? Or how do you get it? Anybody? Anybody want to say? Nope? Too easy? Yes, no.
I think I got the square root of 116.
116. I think you're a little. This is so it's 8. So you get. Let's see. So you need to take. What did you do?
So I put in the first kind of bracket would be -2 minus 8 squared.
Okay. -2 minus 8 squared plus
1 minus 3 squared.
1 minus 3 squared.
So then I got -10 squared
Mhm.
and then plus -4 squared.
It's not -4. You got 1 minus 3, not -1 minus 3. Right. So it's got to be a -2.
So -2 squared.
Yeah.
So then I guess that would be the square root of 104.
Square root of 104. Yep. Okay. Right, and you notice that just observe that if you change the order, it doesn't matter, right? If you say like 8 minus -2 squared plus 3 minus 1 squared, that's still going to be 10 squared plus 2 squared. So you get the square root of 104. Right, so it doesn't matter. Of course, it doesn't matter because you're taking the absolute value. You're taking the absolute value. So if you change the order, you still get the same thing. So, but in case you suspected you didn't believe the absolute value, you see that it actually does work. Okay. Okay. So there are some problems in the book. One of the problems is, do I have a right triangle? So they give you 3 points and they say, do these 3 points make a right triangle? Okay. Okay, so they give you like they give you the coordinates of 3 random points, A, B, C, D, and E, F. Say. And they say, is this a right triangle? Right? And the way you can use that is by using sort of like the reverse of the Pythagorean theorem. So let me just give you this fact. So I don't like doing this, but I'm going to do it. Just take it as a fact for now. I'm not going to explain why it's true. Later on, we'll see why it's true. Okay, but right now, so you know that the Pythagorean theorem says, that if you have a right triangle, if ABC is a right triangle, then c squared equals a squared plus b squared. Okay, but there's also something called the converse. There's also a converse of the right triangle, of the Pythagorean theorem, that says the opposite, right? If you have a triangle, if a triangle has side lengths A, B, C, and c squared equals a squared plus b squared, then it has to be a right triangle. Okay, so you can use, if the 3 numbers form what's called a Pythagorean triple, okay, if the square of one guy is the sum of the squares of the other 2 guys, then in fact it has to be a right triangle. Okay, so you can use this fact to determine whether or not your triangles are right or not. Right? You can say, okay, somebody gives me 3 random points. I can take the distances, so I can calculate the 3 distances, A, B, and C, and then see if b squared is a squared plus c squared, or c squared is a squared plus b squared, or something like that. If the square of one of them is the sum of the squares of the other 2 guys, then it must be a right triangle. Okay, so like I said, this is kind of a, I'm just telling you to and saying use it. I don't like that. Later on, we'll do something called the law of cosines, which shows this, and in fact is sort of like the super Pythagorean theorem. Okay, it's like the super version of the Pythagorean theorem. It works on non-right triangles as well. Anyway, so okay, so that's the kind of problem that you'll see related to this distance formula. Okay. Okay, another thing that is introduced in this chapter is something called the midpoint formula. So it's nothing too fancy. All it's saying is that if you have 2 points, let's call this one A, B again, and this one X, Y, then you can create a formula to find the point that's directly halfway between them. Okay. So what would that formula be? What would that formula be? Can you figure it out? Just think. What would the x coordinate? What would the x coordinate? This thing has x. Let's call these guys C and D, say. And let's call this guy in the middle x comma y. Well, what are the? If I take my here's my point. If I take my point and look at its x coordinate and look at this guy's x coordinate, what's going to be the x coordinate of? What's going to be the x coordinate of the midpoint? Jane.
A plus C over 2.
A plus C over 2, right? It's going to be the average, right? A plus C over 2, right? You take those 2 things and you average them, you get the midpoint, right? Right? And similarly, for the y coordinate, you again take the average, so you get B plus D over 2, right? So it's kind of obvious, right? This is going to be the midpoint is this guy. The average, it's got the thing with the whose x and y coordinates are the averages of the other two guys. Okay. Yeah. So it's maybe not that interesting. They give an application of it, which again is not a real application, but we're going to do it anyway. So they give as an application, so using the midpoint formula for approximations. Okay, so this is not really how you would do it. This is kind of a simplistic way of how you do it, but anyway, we'll do it for now. And we'll get to better things later. Okay, so here's the example. So they say, well, look, suppose you want the square root of 26. Okay, what's the square root of 26? Okay, and they say, well, look, here's the square root. The square root function looks something like this. Okay, and let's see, the square root of 16 is 4. The square root of 16 is 4. And the square root of the square root of 36 is 6. Okay. So you've got these points on the square root function. Well, you know, right? You know that the square root of 16 is 4. The square root of 36 is 6, right? And you want to know the square root of 26. The square root of 26, and so they say, well, it's not unreasonable to take the midpoint, right? So take the midpoint here, right? If this guy is 4, 16, and this guy is, sorry, backwards. This point is 16, 4, and this point is 36, 6, right? Then what's the midpoint here? What's the average of 16 and 36? What's the difference between 16 and 36? 20, right? So halfway would be 10 over, right? So this would be 26. What's the average of 4 and 6? It's 5, of course. Right? And so they say, okay, well, that means that you know, the square root of 26 is something like 5. Okay. Don't like it. Kind of silly, but anyway, that's don't worry, we'll get to much better things later on. Right, but yeah, so this is kind of a simplistic way of approximating things that you don't know. Okay, they give another example. They have some sort of survey. And they say that in 1995, the average math SAT score was 506, and in 1997, the average math SAT score was 511. Okay, and they say, well, what was the average score in 1996? So again, this is a midpoint kind of problem, right? You got in 1995, you got one score. In 1997, you've got some other score, right? And you want to find, you know, the value in the middle. So you take the midpoint of those things. You notice that what's going to be the average? Well, the difference is 5, right? So we'll just add 2.5. We'll add 2.5 to the smaller, or take 2.5 away from the larger, right? So we think that the average should be around 508.5. Okay. So again, this is your midpoint formula, basically. Okay. And in fact, So in fact, the average, in fact, the score was 508, okay, in reality. So you lucked out, you actually got something that was pretty close. Okay, so this is application of the midpoint formula. Is that pretty clear? Okay. Just for your amusement, let me show you how the ancient Babylonians, this is not in your book, but let me show you how the ancient Babylonians calculated square roots. So this is the Babylonian algorithm, Babylonian algorithm. So, thousands of years ago, the Babylonians were able to calculate square roots using a kind of interesting method. So, the way they would calculate the square root of 26 is like this. They would say, well, I want to get the square root of 26, right? In other words, I want to get, if I have an area of 26, I'd like to have a square, right? I'd like to have a square that, and then all I would need to do is figure out the side length, and then the side length would be the square root of 26, right? Because if I've got a square, then the area here, the side length should be the square root of the area, right? Right. So they say, okay, so I'm going to make a guess. My guess is 5. Right, and that guess is, you can make whatever first guess you like, but 5 seems like a pretty good one, because you know that 5 squared is 25, right? So you say, okay, I'm going to make a guess. My guess is 5. 5 is actually, we know that 5 is actually too small, right? 5 is too small because 5 squared is 25, right? So 5 is actually on the wrong side. It's a little bit too short, okay? But still, we make a rectangle of area 26. Okay, we make a rectangle of area 26, and what's going to be the length? What's going to be the length of the other side? If this is 5, then this is the area is 26. What's this going to be? What times 5 is 26? 26 divided by 5, right? So this is going to be 26 divided by 5, right? Okay, and that's actually going to be too long. That's going to be too long. So what do? You take the average of those things. So we know that the 5 is too short. If 5 is too short, then 26 over 5 is too long, right? 26 over 5 is going to be, longer than it ought to be. Okay, so we know that we've got something that's too short for the square root, and we've got something too long for the square root. So let's take the average of them. Okay, and the average is going to be, right? This is 5 plus 5 and a fifth. You divide that by 2, and you get 5 and a tenth. Right, so you get 5.1. This is 5.2, and you get 5.1, 5 and a tenth. 51 tenths. Okay. So does anybody have a calculator? If you have a calculator, what is the square root of 26? 5.099 something, right? So how far off are we? We're actually good down to about the 10,000th place, right? We're off by something in the 10,000th place, which is pretty good, right? So ancient Babylonians. Okay, so yeah, even better. So this is your second guess, and it's actually a little bit big, right? So you can actually keep on doing this. You actually keep on doing this. So you'd say, okay, now I'm going to make a guess, and my guess is 51 tenths. 51 tenths. So So you iterate the process and you do it again. 51 tenths, you say, okay, if this is 51 tenths, then this is 26 divided by 51 tenths. Right, so 260 51ths. Right? Because if I multiply those two things together, I get 26. Okay? Right? And again, you would say, okay, I know that this one was too long, so this one must be too short. So again, you take the average. Right? So you take 51 tenths, right, that's 5.1, plus 260 over 51, and you divide by 2. I cannot do that in my head. This is what my mom said, stop thinking about these things while you're driving. Can somebody use a calculator and divide 260 by 51? What's 260 divided by 51?
5.098.
5.098? Is that it? There must be more than that.
There's more decimals.
Please give me more decimals.
039216.
Okay, thanks. Okay, right. So then you would take the average of those things, right? Do you mind adding 5.1 to that and then dividing by 2? 0.099019608. Thanks. And what was the actual square root? I mean, what was the thing that your calculator gave for this?
5.0990195114.
Okay, right. So you see that second time through, right? Use the Babylonian algorithm second time, and you see that we get a even better approximation, right? So we start making a mistake, right? We need to add something on this at this scale to fix it. Right. Okay. So yeah, pretty cool, right? So if you want to, in case you're feeling down, I recommend this. It's a good method to cheer yourself up. Just calculate square roots in your head. Okay. Okay. So there's another concept introduced at this point, which is the percentage error. Okay. Percentage error. Okay. And that is defined as the absolute value of the error over the absolute value of the actual value. So percentage error of an estimate or an approximation. Okay, so here, right, you've got this estimate, it's 5, right? So you'd say, what's my error? Well, I need to subtract, take the absolute value of the square root of 26 minus 5, and then divide by the square root of 26. Okay, and then that would give you the percentage error. Okay. Similarly here, right, the error was 0.5, right? So here the percentage error is, the difference, so 508.5 minus 508 divided by the actual 508. Okay, so that's the percentage error. If you multiply that by 100, that's how many percent your error is. Okay. I don't think this is that useful, but anyway, this is just a concept that is introduced. It's not. I don't think. I don't. It's not that important. I'd say. Anyway, it's, okay. Okay. so that is all I want to say about, so what have we just been talking about? We're talking about stepping into 2 dimensions, right? Stepping into 2 dimensions, we're talking about the plane, got points on the plane, right? You can talk about distance. Main thing is, talking about the notion of distance between 2 points on the plane. Okay, right. Yeah, that's the main thing, the distance formula. Don't worry about the Babylonian algorithm. I'm not gonna. You don't have to know that. Any questions so far? Okay, thank you. 1.5 graphs. I think maybe a better name for this is 2-dimensional solution sets. 2-dimensional solution sets. Right, so we had, we were in 1 dimension, and we had things like one-dimensional solution sets, right? You had something like 3x equals 5 or something, and then on your number line you had some point, 5/3. You said, okay, this point was a solution set, right? Or you had something like 3x is greater than or equal to 5, right? And you said, okay, this infinite interval was your solution set, right? Okay, so now we're going to do that. All we're doing is doing the same thing, but in 2 dimensions. Okay, so that's the main idea here, right? So previously we were dealing with expressions only in 1 variable, right? We had things like x squared plus 1. Whatever. But now we're going to involve things involving, we're going to have expressions involving two variables. So we'll have equations involving 2 variables. Things like, y, x equals y, right? X equals y, or x plus 2 equals y squared, or x squared plus y squared equals 9, or more complicated things. Okay, so we'll consider now equations involving 2 variables, and what we want to think about is the solution set, right? So just as before, the solution set is the solution set of an equation is all points, but now they're 2-dimensional points, right? So previously it was all points on the line, right? All points x on the line, but now it's all points x, y in the plane. Okay, and let me introduce the notion for the plane. We use this r squared to represent the plane. Okay, so r cross r, right? You've got the real line, and you cross it against another real line, and you get the plane, which you can write. This is the more common way, r squared. But if you called it r cross r, people would also understand that. Okay, so its solution set is all points in the plane that make the equation true. Okay. All points for which the equation is valid. Okay, and we have this thing called the graph, right? And the graph of an equation is just that collection of points, right? It's the same thing as the solution set. All the xy in R2 that in the solution set. It's basically the same thing as the solution set. It's just represented on a graph. Okay, so simple example, right? Your equation. If your equation is x equals y, right? Then your graph is going to be all the points on the plane for which the x coordinate equals the y coordinate. So if this is x and this is y, right, it's going to be all points on the plane for which the x coordinate equals the y coordinate, right? So right, if this is the x coordinate, then it must have an identical y coordinate. So it's got to be here. Right? If this is the x coordinate, it's got to have an identical y coordinate. Right? If this is the x coordinate, it's got to have an identical y coordinate. So and you see that the graph of this equation is just this line here. Right? If similarly, if I had something like 2x equals y, right? If this were my x coordinate, well then double that, right? Double that would have to be the y coordinate, right? So this point satisfies the equation, right? You see that whatever point you choose, you have to take twice that to for the y coordinate for this to satisfy it, right? So you take that would be twice that, and so on and so forth, right? So you get this sort of thing. Slightly more complicated example, if we have something like x squared plus y squared equals 1, and we say what is the graph of that equation? Can anyone name a point that's in that equation? That satisfies that equation? What point satisfies that equation? Jane? 1, 0, right? 1, 0 certainly satisfy that. 1 squared plus 0 squared equals 1. Any other points? Any other points? 0, 1, sure. You can put in negative numbers because you're squaring them. So -1, 0, 0, -1, right? Those are fine, right? So you see that these points are solutions and therefore on the graph, right? Does anybody recognize this equation? What's this an equation for? Yes, Amy?
Circle.
It's an equation for a circle. How do you see that? Well, you can think of this as a distance. This is x minus 0 squared plus y minus 0 squared equals 1. Right? X squared plus y squared, I'm going to rewrite as x minus 0 squared plus y minus 0 squared equals 1. Right? So what's this thing on the left? Does that look familiar? Should look kind of familiar. We've seen something like it recently.
Like the distance formula?
Yes, looks like the distance formula, right? This thing on the left is the square of the distance, right? This is the square of the distance to 0, right? So it says the square of the distance to 0 has to be equal to 1. Right? Well, if the square of the distance is 1, then the distance is 1, right? Or -1, but you can't have a distance of -1, right? So what is this saying is that the distance, right? Let me take the square root of both sides, and it says the distance from your point to the origin is 1, right? So what this says is this this in English, I guess, is this, right? What does it say? You're looking at the points whose distance to 0 is 1. Right? In other words, you're looking at a circle of radius 1. Right? So this is, reading in English, says that the distance of xy to 0, 0 squared, actually, is 1. Right? And so that tells you that you're looking at a circle of radius 1. If I had a 2 over here, it would say that you're looking at a circle of radius square root of 2. Right? If this were a 2, right, if I looked at this thing, let's say, let's make it a 4, right? If this were 4, then we'd be looking at a circle of radius 2. Right? Because this says that the distance squared is 4. The distance to the origin squared is 4. Right? So that tells me that the distance is 2. Right? So that would be this guy here. X squared plus y squared equals 4, and so on and so forth. Any questions? Any questions? Okay. Just one last thing that you've probably seen before. So some more terminology. If you have a graph, so given a graph, the x-intercept is the point on the graph that lies on the x-axis. Okay, so like here, this graph of the circle has 2 x-intercepts, right? This would be an x-intercept here, and this would be an x-intercept. Right, and similarly for y-intercepts. So similarly for y-intercepts. And you see that one can calculate them. How do you calculate? How do you find x-intercepts? Well, you know that the y-coordinate has to be 0, right? The y-coordinate of an x-intercept has to be 0, right? So just substitute 0 for y in the equation and solve for x. Right, so over there, x squared plus y squared equals 1. Right, you'd say, well, how do I find the x-intercepts? Y is going to be 0, right? So y is going to be 0, so you get x squared equals 1, which tells you that x is plus or minus 1. Right? X could be plus or minus 1, y is going to be 0. So you know your x-intercepts are plus or minus 1, comma 0. Right? If I had a line, 3x plus 2y equals 5, then what's the x-intercept? Can somebody just look at it and tell me what's the x-intercept? Five-thirds. Right, so 5/3 comma 0 will be the x-intercept. And what about the y-intercept? The y-intercept, well, x would be 0, right? So what's the y-coordinate?
0, 5 seconds.
5 halves. Uh-huh. 5 halves. Right? Right, so you just say, you let x, to find the x-intercept, you let the y be 0 and solve. To find the y-intercept, you let x be 0 and then solve. Right? And that would give you the x and y-intercepts for this line. We'll get more to lines later, but once you've found out 2 points on a line, you've got the line entirely, right? So that would be enough to draw a picture of it if you wanted to, right? Because you've got you would have found these 2 points, right? 5/3 and then 5 halves, right? So that would give you the line. Okay, that's it for today. I'll open the assignment later. Sorry that I forgot to open it on Gradescope.